Anyway, there was a handout today. Everybody was studiously studying my little article on leadership at MIT. You ready, Brian?
Yep.
Okay, so I often will do a review of what we did last time, assuming that you weren't paying attention. Oh no, or just to tell you what was important. Remember, I think I told the story that there's only a couple of points that a professor can make in an hour, and you have to figure out what the outline is. If you can figure out the professor's outline, then you've got it knocked, okay? But it's sort of this game, they try to hide the thing. But all fusion, last time we talked about all fusion welding processes, in order to get melting, which is fusion, have to have surface heat intensities over only a 3 order of magnitude range. What I didn't tell you is about 1 order of magnitude comes between the difference between melting, just barely melting on one end, and severe vaporization on the other end. It's only about a factor of 10 in heat. To vaporize something takes about 10 times as much heat as to melt something. And if you want to know why, you can take my thermodynamics class. But that's a factor of 10. The other factor of 100 in this range comes from the variation in thermal conductivity of different materials. Okay? So if you go back to the fundamentals of Fourier's first law, you can kind of prove scientifically that it's a fairly narrow range of heat intensities. This end, below this end, you don't have enough heat to melt, and above this end, you have so much heat, the only thing you can do is drill holes and blast things apart, and that's not welding. That's not to say there aren't useful things to do, like drilling holes in turbine blades above this, but we're not going to discuss that in any great detail. However, you can also take that and you can show that you go from a heat efficiency of about 1% goes into melting of 100% of the heat you put into the part to about 99% efficiency. Okay? Your heat affected zone size, well, it's a little more complex. We talked about that. But it is controlled down to this size, at this lower range, by the heat intensity. At the upper range, it's actually controlled by the width of the melted fusion zone, and we'll talk about that some more later. The interaction time, which is just the size of the weld pool divided by the velocity of travel. If I'm traveling along and a weld pool passes point A, the front leading edge, how long does it take before the trailing edge passes that same point? The distance or the length of that weld pool divided by the travel speed is what we call the interaction time. That's how long the heat is hitting that spot, okay, the beam or whatever. The interaction time can go from several seconds here to about 10 milliseconds at this range, okay? And you can actually prove that the interaction time should go as a square of the heat intensity, but that's actually a homework problem. The travel speed is just the inverse of the interaction time. The need for automation, as you get to interaction times less than a few tenths of a second, people can't respond that fast, and so you actually need to automate the process because hand-eye coordination won't do it for you at higher heat intensities. Equipment costs, as you automate, now all of a sudden your big cost becomes automation, and you can change this watts per square centimeter to $2 per capital cost of equipment. Depth to width ratio, one of the handouts I didn't show you last time. This is actually a sample that Hitachi gave me over 20 years ago, but they had a 5 kilowatt laser they had developed, and the first one they actually show you, this is actually a piece of is it lucite? Yeah, lucite. Polymethyl methacrylate. I know the chemical name. Anyway, it's just a piece of plastic, and if you hit it with the laser, you actually vaporize the surface of the plastic, and this is one of the ways they figure out whether you've got a well-shaped beam. And I'll pass this around later when we talk about lasers, but the first one is what's coming out of the tube, and then it's focused, and if they focus it and then also tilt it so that the circle becomes a long ellipse, you get a much deeper heat intensity. If you look along the side, you'll see the difference in heat intensity due to the depth of melting. And you're actually getting a very deep depth to width ratio. That's just showing it to you on something that's transparent so you can see it. We actually have a high-speed video the Japanese put together in the 1980s that you'll probably see one of these days when I'm not here, that actually will show it to you with x-rays on aluminum, and then they laser weld on glass. And so so you can see these things. Anyway, it controls the depth to width ratio. You may have something like 1/5 the depth to the width, or 1/10, all the way up to something that's 10 over here. So 1/10 to 10 as you go across there. And production volume requirements. When you get travel speeds as fast as you can get with laser and electron beam, then you really have to have a lot of material, or you have to have a very high value added part, such as the aerospace industry. So see, it's a very simple concept. You just start with, what can you say about something when you don't know anything about it? You start with Fourier's law of heat conduction, and you think your way through this, and you can draw all kinds of conclusions. So a number of years ago, 10 or 12 years ago, 13 years ago, when the Navy had these particle beam weapons, they wanted to know what to do with them, and they called me down and said, to White Oak, Maryland, and said, what can we do with these? And I said, you could melt a submarine. Because I was actually thinking, and actually they asked me to give a presentation, and I gave them the presentation I gave you yesterday, okay? Because they're a bunch of physicists, they'd never thought about those things. And all I had to do was figure out where in the spectrum their new heat source lie, and then I could tell you what the characteristics of it were going to be. But if it didn't lie between here, it was actually going to be no good. Well, in fact, it was a pulsed heat source, and in some ways it could go all the way up to 10 to the 8th, and it had 5 megawatts of power. So I mean, it was a huge heat source, but you could scale it back, and we can talk later about what we ended up doing with it and whatnot. But so that's a review of what we did. Now today we're going to start right here at 10 to the 3rd, and over the next few classes we're going to march through these processes to get up here to, and we're going to discuss, today we're going to talk about, zoom up a little bit, we're going to talk about flames, okay, I'd say settling flames, and the next class we may have in here with me live, I mean you'll have one on Wednesday, you have no class tomorrow, but you have come after your quiz. Wednesday, you'll watch a video on one of the other modules, so you'll probably be doing friction welding or something, solid state bonding or something. But the next time that I lecture, we'll probably be going through either finishing up cutting, or we'll get to arc welding, and we'll do that for a while, and eventually we're going to work our way over here to laser and electron beam. So we're going to work our way, I've given you the overview now, we're going to work our way across there and see what's going on. Now, flames. Flames are sort of interesting, and we're all generally familiar with flames. Actually, I can go back and put this up. This is an air, fuel, gas flame, like a Bunsen burner in high school, okay? And you'll get about 100 watts per square centimeter, and you know you don't melt steel in Bunsen burner because, if you remember, you put the Bunsen burner under the ring stand, you had these little things that you would put the glassware on, and those things were actually made out of little steel wires, and they didn't melt, okay? If you could melt steel with a Bunsen burner, that wouldn't have worked very well in high school chemistry, right? Now, that's actually what we call a premix flame, and I'll describe that in a little bit. But if I go down here 2 orders of magnitude away, and I have a candle, well actually candles, depending on the candles and the size of the candle, and the weight of the hydrocarbon fuel in the candle, paraffin wax. The candle might have anywhere from 1 to 10 watts per square centimeter. And how do I compare that to something that you know about? A bright sunny day is about 0.03 watts per square centimeter. Okay. You're actually, when you burn the leaf on the sidewalk with your magnifying glass, you're just concentrating the sun's rays. And so if you increase it by a factor of 30, you get to essentially the heat of a candle. So you can burn the leaf just like you can burn the leaf with a candle, right? So with a magnifying glass on a sunny day, you can start a pile of leaves on fire, right? So these numbers sort of work out. There is an article, and in fact, this graph that I showed you originally was drawn by a guy named Anderson. His paper, you have inside all your stuff somewhere. I'll find them later. John Anderson is an MIT chemical engineer who actually first pointed some of these things out to me and did some research on some of these things. But anyway, what makes flames flames? Well, we often talk in flames about combustion intensity. The combustion intensity, which has watts per square centimeters of units, is equal to CH times CV, where H stands for enthalpy. Does everyone know what enthalpy is? You had a thermodynamics course somewhere in your life. Enthalpy you can just think of as heat. Okay, all right? Yeah. So, enthalpy is a thermodynamics word for heat. Okay. So there's a certain enthalpy of the reaction, and there's certain gases that burn hotter than others, and so the intensity of the heat from a flame is going to be dependent on the heating value of the gas. And that enthalpy is going to have units of joules per cubic meter. And there's also the combustion velocity. And that has units of meters per second. If I multiply all this together, I get joules per meter squared per second. Anybody know what units those are? Watts per square meter, which is sort of like watts per square centimeter. Okay? If you go to the flames business, they talk about combustion intensity. Now you have to be careful. If you go to the boiler business, they talk about a combustion intensity which is not a surface heat flux. They'll talk about a combustion intensity in terms of per unit volume, because you're talking about the volume of heat in the boiler. Okay, they define it a little bit differently. But it's basically the same thing. There's an enthalpy of the reaction, how much chemical energy is being released by burning the fuel, and different fuels have different enthalpies. And what's the speed of burning? Now, has anyone ever heard of burning velocity? Some of you guys have dealt with explosives. You've heard of explosive velocities and things like that, right? In fact, if I take the torch, and I may have to turn the lights off, make this a little bit easier. But right now, the combustion velocity is faster, or the gas coming out is faster than the combustion velocity. Otherwise, if the combustion velocity was faster than the gas, it would burn back. And in fact, if I turn this off, if you look right down here where I'm actually mixing the gas with the air, these little holes down here, you should see a little flash. You see the little flash? That's because when I turn it off, the velocity has to go to 0. And if the velocity goes to 0 of the gas coming out, the combustion velocity now exceeds it, and it burns back to where the gas was coming out. And you saw the little pop there at the end, which will always happen. It's an experiment that usually doesn't fail. Now, there are basically 3 types of flames in the world. There is the candle flame, or the sit around the campfire flame, or the flame that you get in your fireplace at home, and it's called a diffuse flame because you have fuel and you have oxygen or air, and they're coming in and they sort of mix together and diffuse together out in the open atmosphere. So if you look in the fireplace, you get this nice wispy flame, you know, going back and forth, and that's because the hot gases from the wood or whatever you're burning in your fireplace have to diffuse in with the air coming in. There's nothing controlling it to keep it focused in one area. It's not pre-mixed, and the burning velocity is relatively low because you don't have optimum mixtures of fuel and air. You have whatever mixture will burn and whatever statistically kind of comes together with the right burning velocity, and you already have pre-ignition from something this flames have been going on for a while. And so that's a diffuse flame. A candle, although the candle is sort of, with a candle you've got a wick and it's creating a vapor from this little liquid pool. Remember, it's not the solid candle wax that burns. It's not the liquid candle wax that burns. It's the vapor that comes up the wick. In general, it's gases that burn. If you start figuring out how many molecules you've got, you don't have enough molecules on the surface to get all the oxygen to the surface to burn, or of either a solid or a liquid. It really is a gas. And so we might think we're burning paraffin wax, but in fact, we're melting the wax. It forms a little puddle on the top. That little puddle, the wax comes up the wick and vaporizes as the wax vapor that's actually burning. And that's true of wood. It's the vaporizing wood, okay? The hydrocarbons in the wood that are vaporizing. The next level, and this is low velocity. And this low velocity, even if I have a decent enthalpy, the fuel is a decent fuel. Paraffin wax is the same as ethylene, okay? C2H2, or not C2H2, C2H4 or something. CnH2n plus 2 is the official formula for paraffin, but it's also the same formula for polyethylene and other things. You have a reasonable enthalpy, but you have a lousy velocity because you're not burning things at their optimum ratios. You're not pre-mixing them. A pre-mix flame, which is what this guy is, and where's the mixing chamber? Here. In this, you got a little orifice right here where the gas comes out, and then I have these 4 holes where the air comes in, and the mixing chamber is this tube right along in here. It mixes in here, but it doesn't burn until it gets out, as long as I've designed the whole thing so that the burning velocity is not greater than the exit velocity. Okay? If I don't design my torch with the right size orifice and air holes and everything, I won't get a good mixture close to the correct mixture of fuel and oxygen. But if I do, I'll have mixing of the fuel and the oxygen inside a chamber at essentially constant pressure. Okay? So this is constant pressure mixing, but no ignition until I get out here. But when it ignites, it's already mixed. There's no need to diffuse oxygen, and so it burns with a nice uniform flame. And if you look at the flame, you'll see actual different regions. This might be a hotter region where you get carbon monoxide when you burn the hydrocarbon, and out here you'll burn the carbon monoxide, so you get kind of different layers to the flame, and there are whole books written on that. Okay? The velocity here, if this is 1x, this is probably 10x or more. And so it turns out the premixed flame has a combustion intensity probably 10 times greater than the diffuse flame, maybe 100 times greater, depending on the fuel and everything. Well, I told you, if I put this back up, that a candle was 1 to 10 watts per square centimeter, and this air fuel gas flame, like the red propane torch there, is 100 watts per square centimeter, where there's my factor of 100. Okay, it may be a slightly hotter fuel. Propane burns a little hotter than the candle wax, but also with that premixed chamber and everything designed well, it's got a much higher velocity, and so it has a factor of 10 to 100 greater heat intensity. So I guess I can leave that up. And the last one is a jet burner, which we don't use very much for welding. We usually use premixed flames. But a jet burner, you have fuel, you have oxygen, and you ignite it at constant volume. And here I can have anywhere from 100 to 1,000 times the heat intensity, or the burning velocity. It's ignited at constant volume and it comes shooting out of here at very high velocity. It's a jet engine. Okay? So those are the 3 types of flames. This is the one we're usually interested in welding, is the premixed flame. But flames go over a tremendous variation in combustion intensity, from something like 1 watt per square centimeter to something on the order of 1,000 or 2,000 watts per square centimeter. Okay? Now, if remember up here, I told you that the, if you have questions, stop me, okay? I told you that the heat efficiency for flames was about 1%. If you actually calculate a theoretical combustion intensity, so I've got my torch, let's consider this a torch that's shooting out gas against the surface, and I figure out how much energy is hitting that surface versus how much is being transferred by heat, of that heat is being transferred into the surface, I find it's only about 1% efficient. It turns out 1 or 2% efficient. It turns out for this pre-mixed flame, this guy right here, this is an air fuel flame. It's got a heat intensity of about 100 watts per square centimeter, but only about 1 watt per square centimeter of surface actually gets transferred, maybe 2, into the metal. So the theoretical heat flux is about 10 to 50 times, or is 2 to 50, 2%, 1 or 2% of the total heat generated chemically is actually getting into the metal. Does anybody have any idea why it's so inefficient? Yeah.
Maybe the air absorbs a lot of energy.
Well, it has to do with the air, but it actually has to do with how the air flows on the surface.
I was going to say that as well. I guess the air is just as an insulator.
That's right. That's exactly right. The air forms a boundary layer. You ever heard boundary layer? Who has not heard boundary layer in here? Don't. It's okay to raise your hand if you're a mathematician by undergraduate background. Sounds to me like you've got mostly engineers or mechanical engineers or aeronautical engineers or something, and you guys have heard of boundary layers. But basically, if I have a jet of air hitting a flat surface, I'll have, this is the surface down here, okay, I'll have a boundary layer forms. Right here is the stagnation point, and just kind of a review. You guys are going to get this in spades when you do your fluid flow, right? Around propellers and things like that. But you have a boundary layer, and this is relatively stagnant air. If you remember from having studied boundary layers, you draw the velocity profile, it's zero velocity up to a free stream velocity. So if the air is coming in like this and going out, or the fuel air mixture, the hot gas is coming in, hitting the surface and turning the corners, you have a free stream velocity, but down in the boundary layer, the velocity drops to 0. And this becomes sort of an insulating layer of air. And the heat transfer across that boundary layer limits the heat conduction from the hot gas to the condensed phase, solid or liquid, whatever it is. So I'm boundary layer limited in flames, except in 2 cases, which we'll talk about. Tricks of getting around the boundary layer that we use in different things. And so even though I have 100% of my heat coming out of my nozzle, I only get about 1 to 2% of my heat actually transferred into my solid or my liquid condensed phase. And most of it just goes to heating up the welder. Okay, if this guy's an oxy-sending welder, just heats up his environment and makes him sweat. Yeah.
This happens with all the gases or only with the air?
It happens with gases. Any gas, whether it's air or anything else, will form a boundary layer. If you have it hitting a solid surface and then turning the corners, you'll form boundary layers. If you're now looking at heat transfer from a hot gas to a cold surface, you're going to find that you essentially insulate the surface and you are limited by your boundary layer thickness. And so one way, how do you get a thinner boundary layer? Higher velocity, right? So if I go back up here, velocity turns out to be very important, okay? It turns out the enthalpy is related to the temperature of burning of the gas, and the velocity is also related to the temperature of burning of the gas, okay? There's an expansion of the gas, which gives me the velocity of burning, which is related to temperature. PV is equal to nRT. And there's also how much heat I'm generating, which is just the enthalpy of the gas times the heat capacity times the temperature, right? So it turns out the combustion intensity goes as T times T, because C sub H is proportional to T and C sub V is also proportional to T, and the combustion intensity is going to vary as, shouldn't be equal, it's going to vary as T squared. Okay? A little bit more temperature can do a lot for me. Was there another question?
Yeah. For some reason I'm just not seeing this. Why, what keeps, if we were to ignite the gases in your propane torch
Yep.
in the combustion chamber, what keeps that from being a little tiny little jet engine?
Oh, I'm not igniting it in the combustion chamber.
Right, if we did though.
Oh, if you did, it would be a little jet engine. You're absolutely right. If I designed this thing such that I actually had ignition inside here, it would come roaring out at about 10 times the velocity. Because right now,
That's not
when
the same as just sticking your little igniter halfway down the tube.
if I move my igniter down here, I would start getting a poor man's jet burner. Okay, it wouldn't be well designed, because I'd have to change the nozzle size and everything else. Right now, the velocity of this coming out is basically proportional to the pressure of the gas coming through that orifice and how much air it's dragging in with it. So it's the cold temperature, it's the cold velocity of the gas that's coming out, okay? And that velocity of the gas coming out has to exceed the combustion velocity of this fuel, which is characteristic of the fuel in the oxidizing medium air in this case.
Otherwise the fuel would go right back down to the...
Right, if it goes back down, you get a jet burner, and that's where you start, momentarily you hear a pop. If I could sustain the ignition, it's not easy to sustain the ignition in a jet burner. Usually they blow themselves out, they flame out. They call it flame out, right? They blow themselves out. You have to design a jet burner fairly carefully so that you can sustain ignition and it doesn't blow itself out. You have to have the fuel air coming in at just the right balance and just the right nozzle design in order to run it continuously. Otherwise, it likes to blow itself out. Okay? Yep.
I was going to ask some pyromaniac, if you had that and you actually had it going and you stuck a match inside that combustion chamber,
Yeah.
that's you would get the jet burn basically out of it?
For a second. But it's only, it's not, this is not designed to sustain continuous jet burning ignition. Okay? I could design it that way, in which case I have a jet burner. When I say a poor man's jet burner, this is not designed to be a jet burner. Okay? If it had been designed to be a jet burner, then I could get it, and all of a sudden you'd hear a roar coming out of here. Why? Because when it's a jet burner, I'm getting the burning velocity of the hot gas, not the cold gas. And that's about a factor of 10. And now I hear loud noises because I got all kinds of shock waves as these things swirl around.
What's the principle of an afterburner then?
An afterburner is just a jet burner. You add an afterburner after a jet burner, essentially as a second thing where you inject fuel into this. Okay, so you have to have some air come in here too, because if you just inject fuel and there's no leftover air from this, then you have to have some excess air and fuel. But this is your ignition source, and it's coming out at high speed. Now you're essentially putting a jet burner behind a jet burner and getting that extra boost and burning fuel like mad.
So it's a constant volume then too, the afterburner?
It's sort of a pseudo constant volume. I mean, it's constant volume on 5 sides, but the 6th side is a hole that is shooting out, right? If you did it and you closed off the end of it, you'd have an explosion and the whole thing would go boom once, right? Okay, so it's not really constant volume. This is not really constant volume, but you've got a nozzle that makes it nearly constant volume. An afterburner, you got a nozzle the size diameter of the engine, and you're pumping fuel in there, not in a little combustion chamber this size, but a combustion chamber this size, which is why it burns so much fuel. And it doesn't burn it at stoichiometry either. I mean, the engine is designed to burn at something closer to stoichiometry. The afterburner is just a can, and you're just doing a sort of controlled explosion, continuous explosion. Okay. Yep.
So the question, what's stoichiometry?
Stoichiometry is having the right fuel-air ratio so you don't have any leftover fuel or any leftover oxygen. And in fact, it's a very good lead-in to one of my next things, which is on the order of my stuff. Take it back with this. Okay, if I put this up, this comes actually out of the welding handbook for flames. This is normal combustion velocity versus fuel in mixture by volume percent. And I have acetylene, I have propane, and I have natural gas. And it has stoichiometric mixture, neutral mixture. Neutral mixture is where there is no excess oxygen, supposedly. Stoichiometric is where theoretically you have just the right ratio, number of moles of oxygen to number of moles of fuel to burn it completely. So stoichiometric mixture is perfect ratio of gas to oxygen. The neutral mixture is where you essentially get, in a sense, a practical flame that's neutral. In most cases, there's not a big difference. In acetylene, there is a difference. But you'll see that the maximum temperature changes dramatically, or burning velocity, and the plot for temperature would look very similar. If you get off of stoichiometry, you have excess fuel on one side, or you have excess oxygen on the other side that's not being burned, that has to be heated up. You've got all this excess baggage. Okay? At stoichiometry, you're burning everything, and you don't have anything that goes through there acting as if it was inert. And somewhere here. In So, the things that determine temperatures of the flame are the enthalpy of the reaction. Sorry, Brian, I can't see that. Enthalpy of the reaction, whether it's stoichiometry, which is, if you will, fuel-air ratio.
Is that fuel-air ratio a constant number for any combustion?
It depends on the fuel. It's a different ratio for every fuel. I'll show you in a second. And 3 is how many inerts. For example, if I'm burning in air, I've got a lot of nitrogen that doesn't burn, it just gets carried through. Okay? So let me, since it doesn't work on the video, let me write down a formula. If I'm dealing with acetylene, which is C2H2, and I'm going to burn it in pure oxygen, it's going to form, in the simplest sense, CO2 plus H2O. And so that's going to be, oops, there's 2 carbons, so there's 1 hydrogen, so it should be 3 of these. 3? Did I get that right? Anyway, you can balance it. Okay. 2 oxygens, 4 oxygens. Okay, so I had to have 6 oxygens, right? Is that right? Yeah. 2 carbons, 4 oxygens with the CO2, 2 oxygens with the hydrogen, and oh wait a second, I got too many hydrogens. Is it 3? 5 halves. Is that right? There we go. Something like that. You guys can balance it. Do it as a homework problem. Anyway, so that would be stoichiometric. If I actually burned it in air, I would have nitrogen, and I'd have the same amount of nitrogen on both sides. And in fact, for every mole of oxygen, I would have 4 moles of nitrogen. And that gets carried along. And that drops the temperature significantly because I have to heat up all that nitrogen. It's not giving me any enthalpy. Okay, so inerts lower the burning temperature. Being off stoichiometry gives me excess oxygen or excess fuel, which doesn't give me any contribution to enthalpy. So I end up with these types of plots where if I'm at stoichiometry, I'll get the maximum temperature or maximum burning velocity. They go together. And you have these plots in your handouts. That's how I get my maximum temperature. That's how I'm going to get my maximum heat intensity for burning. Is that? Someone said they were confused before. Does that make it clarify? Okay. So you've got to have high enthalpy, proper stoichiometry, and as little inert gases as possible in the whole thing. So the idea is to try to get the highest temperature gas you can. And it turns out the highest practical temperature gas is in fact acetylene. And it's C2, well, let me actually, C2H2, but it's C with a triple bond with a hydrogen on each side. Okay? That's acetylene. And the triple bond gives me one of the highest enthalpies because the triple bond is least stable. And if I go to that same handout that you've got and this is burning temperature, maximum stoichiometric temperature for different fuel gases as a ratio of carbon to hydrogen. Acetylene is 1 hydrogen to 1 carbon. Okay, CH ratio of 1. Acetylene has a burning velocity of something around 3,100 degrees centigrade in pure oxygen. Propadiene, and propadiene, for all you chemists, anybody in here a chemist? No one helped me balance the equation, so I'll assume none of you are chemists. Propadiene, the propa, or the pro, is sort of like propane, and that means it's got 3 carbons. I'm sorry, it shouldn't have triple bonds. It has 2 double bonds. A diene has double bonds, and to balance that, I have to have 4 hydrogens. So propadiene is C3H4, and there's also a variant of that, same C3H4, which is a triple bonded carbon with 3 hydrogens to this carbon, oops, sorry, to 1 hydrogen on this side, and 3 hydrogens, oops, what am I doing? Oh, now I gotta have another carbon. Now I have, yep, 3 hydrogens. So this carbon has 4 bonds, this carbon has 4 bonds, this carbon has 4 bonds with hydrogen over here. This is C3H4, this is C3H4. This has 2 double bonds, this has a triple bond and a single bond. Okay? Now, this is called methyl, here's your methyl group, acetylene. Okay, this is acetylene with a methyl group over here where you would have had a hydrogen. So this is methyl acetylene, this is propadiene. If I put those together, Ma for methyl acetylene with a P, and put another P so I can put a registered trademark up here, is MAP gas. MAP gas, you can go to the hardware store, or you could go to the hardware store until this past March, and buy a yellow tank of MAP gas. Okay, and MAP gas is second only to acetylene as propadiene in terms of burning temperature or velocity. Propylene, which is, it's going to be another triple bonded carbon, if you will. Propylene is 2 double bonded carbons with, is that right? I think that's propylene. Anyway, let's do it. no, that's methyl, that's propionate. Oh, propylene, I think. I don't remember, oh, I remember propylene now. Propylene is, got an H in there, maybe an H in there, carbon,
Too much phone.
pardon me?
The second,
There's only one hydrogen in here. Anyway, propylene's got a double bond in here with the carbon, if I remember. I'll have to go look up propylene. Anyway,
You asked about the map gases out of Massachusetts then? Because I think we can still buy in other states, right?
no, as of early March, the company in Canada that made it went out of business, okay, because of some environmental regulations.
So what are plumbers using to solder joints?
They're now using, if you go, you will now find, I can't remember what they call it. They don't call it, MAP is a registered trademark, okay? But this is just as of this past March. And the plumbers are using basically a propylene mixture, a mixture with some other things. But actually, even this MAP gas has got some other hydrocarbons in it. It's not pure MAP gas. But it does burn hotter.
Not hot enough to weld though, is it?
Pardon me?
Is it hot? It's not hot enough to weld though, is it?
Oh yeah, it is. Just barely. We're going to talk about that. And we're going to do a demo. Which one is louder? Vote for yellow. Why? Hotter, higher burning velocity, more noise. Okay? I can also prove it to you, which I'll do over here, just because I don't want to burn the papers. With a piece of steel. And what you want to do is see which one glows red first. Yellow wins, once again, right? Now you also notice this one burned with a yellow flame. This one didn't. Anybody know why? Yeah.
It's the metal burning, right?
No, it's actually the fact that this one did not get complete combustion, and there's some carbon powder. And it's the carbon that glows yellow in the flame. When you see yellow flames, it means you have an excess of fuel. And by putting this in there, it actually cools this down enough so I'm not getting the proper ratio. That means these torches are actually designed really for propane. I mean, they're rated for MAP, but you can only optimize for one fuel in the torch design. It's the exact same torch, okay? And it's really optimized for this. I can put this in there and it still doesn't have an excess of fuel. This one, cooling it down, the cooling effect on that flame actually turns it, makes it so it will start burning yellow. Okay? Whereas this one does not. Until a little bit later. Okay? But anyway, there is a difference. Okay? Now the difference, make sure I don't burn something up here. Don't anyone tell the safety office. Okay. You got different things. Hydrogen, by the way, is way down here at a 0 ratio of carbon to hydrogen. But hydrogen actually has a much lower burning temperature than carbon. Okay? A lot of people don't realize that. About 300 degrees difference. Now, I just turn these off for safety's sake. And we now can compare. The question was, can you weld with MAP? And the answer is yes, you can weld with MAP. But not as well as with acetylene. Because I told you that the combustion intensity goes as T squared. Somewhere around here. Right here, right? And acetylene oxygen. That was MAP air, about 100 watts per square centimeter. It's not around 1,000. I need 1,000. Turns out acetylene oxygen is around 1,000 watts per square centimeter. And so I should be able to melt steel. It has a combustion temperature, maximum stoichiometric temperature around 2800 MAP, which is going to be just under, but on the order of 1,000 watts per square centimeter. It turns out you can weld with MAP, but instead of having a 2 or 3 second time constant, this may have a 3 to 5 second time constant, depending on the torch and everything else. It doesn't have quite the heat. It is 2870, according to the literature. And the useful heat for melting is just the excess temperature above the melting temperature of steel, which is 1600. And if I take that and square it, and I take 2870 minus 1600, and I square that, everyone see what I'm doing? This is just how much enthalpy I've got above the melting temperature of steel. So now I got to look at those differences and square those, and that works out to a ratio of 225 to 161. So acetylene is 50% more efficient than MAP for melting steel. Okay? So they're both capable of giving me about the right heat intensity. That was an order of magnitude plot, let's face it. Okay? It's not exactly 1,000. This one's going to be slightly less, but it's going to be 50% less efficient for melting of steel.
In terms of cost, how do the two compare?
Depends on how you buy it, and we actually will get into that. I can talk about some of it now. Acetylene has a problem in that it can't be pressurized above 250 psi, and most of your cylinders for high pressure gas are, more like you'd like to have them 2,000 or 2,500 psi. The problem is acetylene becomes unstable and goes boom above 250. So you actually have to either generate your acetylene on site, which you can do. It's relatively easy to do. Most shipyards do it on site. Because to transport acetylene, you have to do it in a cylinder like this, and I'll pass this around next time. This is in the class right now. But this is a cross-section of a B cylinder for acetylene. I'll tell you what B means in a second. But it actually, the acetylene cylinders, tanks that you see, are actually filled with a calcium silicate ceramic that's 92% porous. It's only 8% solid here. It looks solid, but it's very porous. And the rest of it's filled up with acetone. Acetone is a liquid, very flammable, but the acetone will dissolve 400 times its weight in acetylene without high pressures. So you can have an acetylene tank that's only 100 psi but stores a lot of acetylene, but it turns out the tank is very heavy because it's filled with liquid, not gas. Okay? So acetylene is cheaper to produce than MAP, but it's more difficult to transport. So if you want to generate it yourself, you do it the same way that, what's his name? I'm going to find that stuff now. Here it is. Okay, acetylene gas was discovered by Edmund Davy in 1836. But it was not until 1862 when Wohler's discovery that acetylene gas could be produced from calcium carbide that the gas became well known. These developments were of little consequence until 1892 when Thomas L. Wilson of Spray, North Carolina, if you go look up Spray, it's out near the Outer Banks, okay, invented a process for producing calcium carbide. Well, this was 1892. This was after Edison and Westinghouse, and they actually had a source of electricity. And what he did is he was just taking things, different compounds, different minerals and stuff, and sticking them in an arc furnace. And what he did is he put some limestone, which is calcium carbonate, in with some coal. And he started an electric arc in this furnace. And it turns out he didn't know it, but he produced calcium carbide. And when he opened up his furnace, he saw this kind of black-gray powder. and he couldn't figure out if it was calcium carbide, that the calcium carbonate had reacted with the carbon in the coal to form calcium carbide due to the electrical energy in the electric arc. And he couldn't figure out much of anything to do with it, so he went, and back in those days you didn't have the EPA, so he just went down to the river to dump it in the river. And apparently there was an ignition source nearby, because when you take calcium carbide and mix it with water, you get acetylene.
Set the river on fire.
He set the river on fire, exactly. Okay? Plus CO2. Then you can balance it. I'll put an X and a Y there. Okay?
That's what coal miners used to wear on their hats, right?
Yep.
Back in the day.
Yep. And it turns out, by 1895, which is only 3 years later, acetylene gas was becoming recognized as a valuable gas for lighting. So why is this called a B cylinder? B stands for bus. And buses needed headlamps so they wouldn't run into people, or people wouldn't cross the street in front of them in the dark, or would see them coming. And they had 2 B cylinders on the front of every bus in the 1890s in order to be the headlights for the bus. That's why it's called a B cylinder today. Isn't that a wonderful piece of trivia? Next time you're at a cocktail party, you can say, well, you know why it's called a B cylinder for a cylinder? Anyway, it turns out that Thomas Spray got together, it says until 1904, no suitable acetylene container had been developed. I'm sure they blew up a few labs pressurizing it. The gas was used mainly for illumination and was generally piped directly from generators in the area to be served. In that year, in Indiana, P.C. Avery displayed to 2 of his home state's most famous promoters, James Allison and Carl Fisher. Allison in Indiana. What else is called Allison in Indiana? Detroit Diesel Allison. Okay? Allison engine, that was James Allison. And Carl Fisher. Now you don't hear this much anymore, but General Motors used to have all their bodies used to be made by Fisher bodies. Okay? That's who Allison and Fisher were. But anyway, they started a company called Prestolite, and that later became the Linde division of Union Carbide, which after Bhopal became something else. So, whatever. Isn't it wonderful? History wonderful? But one of my stories is I was down at Newport News once, talking to one of the welding engineers, and they had the shipyard as calcium carbide. They have a calcium carbide shack, and they have a little generator, which is nothing more than a steel tank. You put the calcium carbide in, and you drip water on it, and you take the acetylene off the top, and you pipe it around the shipyard at less than 250 psi. And he was telling the story. He was in the welding engineer's office, and some guy came in, and he had just heard the fire alarm go off, and the guy came in. And he says, "What's the fire alarm for?" The guy says, "Oh, there's some fire down at the carbide shack, but it's okay. The fire department's on its way." And that welding engineer shot out of there to beat the fire department to the carbide shack, because it would not have been a good day if they started putting water on the carbide in a fire. So anyway, which one's cheaper? It depends. Are you going to use it locally? Do you have to transport it? They're competitive, except MAP is no longer made as of a few months ago. But you can still buy propylene, which is not really good enough to melt steel. I mean, if you were an oxyacetylene welder and you were using propylene, you would be real bored, okay, or tired of holding that torch, okay. So acetylene is, now that MAP is no longer being made for whatever these environmental reasons were in Canada, basically acetylene's it now, but it's only about March. Okay, I'll see you Thursday.